Hi there, Andy Warwick here with my third video on a cultural history of theoretical physics. In this one I'm going to continue my story of the Poynting vector and say a bit about what I mean by a cultural history of physics. In June 1884, the 34-year-old Oliver Heaviside independently published the energy flow theorem. Heaviside left Camden House Grammar School aged 16 with an elementary knowledge of mathematics. He didn't go to Cambridge. He wasn't tutored by a famous coach. He never sat a Tripos exam. He didn't play competitive sport. Heaviside was a sickly child. He wasn't tutored in Maxwell's treatise. Heaviside published in a trade journal, The Electrician. And like Einstein, Heaviside's been called a lone genius. The young Heaviside was given a job as a telegrapher by his uncle Charles Wheatstone. He progressed quickly, learning everything electromagnetic in connection with telegraphy. In 1868 he landed a job in Newcastle on the newly laid Anglo-Danish submarine cable. He was an ambitious electrician who improved the design and use of the Wheatstone Bridge. For him, the cable was an experimental object of international dimensions. He wanted to know how it worked in order to improve it. Why did signals travel more easily in one direction than the other? Why did the signals sometimes improve just before the cable broke? Could you send more than one signal down the line at once? In 1873, his interest in instruments led him to Maxwell's treatise. It's not a textbook. The treatise is a 900-page compendium on electricity and magnetism, including the design of instruments, electrical standards, and numerous practical applications and problem solutions. Tucked away at the end, untrumpeted, are the general equations and the electromagnetic theory of light. It's an extremely hard book to navigate. For a decade, he struggled to master Maxwell's equations using Cambridge textbooks. For example, he used Peter Guthrie Tait's Introduction to Quaternions, Tait was the senior wrangler of 1852, to express fields and currents as vectors. A long-running investigation of how energy moved around a cable led him to the Poynting vector. One might say that an electrician with his unusual interests was bound to find it sooner or later. Heaviside worked in a subculture of his own. Suburban reclusive, electrician, extramural Cambridge student whose problems came from cables. His energy flow theorem inspired him to recast Maxwell's theory as vector equations in electric and magnetic force, from which he laid the foundations of line transmission theory. Within carefully manufactured, protected, standardized cables, Maxwell's equations became entangled in international communications. Along with them, the energy flow theorem went global too, carried by the interests of imperial management and capital. In the treatise preface, Maxwell said the application of electromagnetism to telegraphy had reacted on pure science by giving a commercial value to electrical measurement and affording electricians the use of apparatus on a scale that greatly transcended any ordinary laboratory. The demand for electrical knowledge had greatly stimulated the energies of advanced electricians. As I just noted, the demand Maxwell spoke of was from London capital to link the world's commodity markets and from London's imperial leaders to tighten their grip on their worldwide colonies. In the graphic, you can see Britain's telegraph network encircling the globe, and Oliver Heaviside and J.H. Poynting. In the last third of the 19th century, the burgeoning departments of Maxwell's treatise were redistributed among new subcultures. Experimental electricity to the Cavendish Laboratory, electrical standards to the new National Physical Laboratory, line transmission theory to new departments of electrical engineering. In Cambridge, Heaviside's homespun physics was rejected until it could be made rigorous by wranglers like Thomas Bromwich and Harold Jeffreys. It was in Niven's Trinity College classroom that the pure theory of Maxwell's general equations began to emerge. Students like Joseph Larmor and J.J. Thomson showed how they could be applied not to undersea cables, but to the electromagnetic theory of light and to the electrodynamics of moving charges. In the 1890s, Larmor developed an electronic theory of matter based on a dynamical ether, the first theory of everything. When it predicted that matter must contract in its direction of motion through the ether, thereby explaining the null result of the Michelson-Morley experiment, the theory was confirmed. On the graphic you can see a tripos problem set by Lama requiring students to prove the contraction of moving matter in the way set out in Lama's textbook Ether and Matter. Via coaches, lectures, textbooks and examination problems, the electromagnetic ether was a taken-for-granted object to Cambridge students, one that gave a dynamical foundation and a unity to physics. That's why they were disbelieving when a Swiss patent office clerk said there was no true rest frame and the ether was therefore superfluous. It was a clash of very different cultures. So why have I called this a cultural history of theoretical physics? Because I placed the work of Einstein, Poynting, Heaviside in separate cultural worlds. Inside each, the things philosophers like to point to explain science, reason, logic, method, and so on, was certainly in operation. But between these worlds was a deep incommensurability, as Thomas Kuhn called it. Poynting and Heaviside found their way to the same equation through quite different research agendas, though using some common resources. In fact, they disagreed sharply about how the vector was to be interpreted. Einstein, a bit like Heaviside, lived in a world of his own making, an idiosyncratic world. To find the order he wanted, a physics based on principles that abolished asymmetries as he saw them in electromagnetic theory, he was prepared to abandon age-old common sense notions of absolute space, time and simultaneity, and the very idea of a universal ether. In Cambridge, that was unacceptable. That elite institution had a powerful educational economy to defend its view of the world, one intended to offer a rational understanding of the universe based on common sense notions of mechanics and dynamics. Now, if you followed these videos so far, there ought to be an important question that's worrying you. If Cambridge had so much institutional inertia and was so hostile to Einstein's physics, how come by the 1920s and 30s it had become one of the most important places in the world for teaching and researching Einstein's theory of relativity? If you want to know my answer to that question, I suggest you read the final chapter of my book, Masters of Theory. Thanks for watching.